What is up, amigos? Today we're talking about how to create objects in potential flow. So over the last few weeks, we've gone through all the really fundamental aspects of potential flow in terms of what stream functions are, velocity potentials, all that kind of stuff. Now we're going to combine all of them to show you how to actually approximate actual objects. So let's start off first with two fundamental flows. A free stream flow, just a uniform flow, as we've covered in this video. And we also have a source here, which we've also covered in this video. And the stream functions for these two in radial coordinates are, in polar coordinates, sorry, are v infinity r sine theta for the uniform flow, psi, and then for the source, psi equals lambda, the strength of the source, divided by 2 pi theta. Now, on their own, they don't really seem like too much, but let's add them together. So let's say we have a flow, and then we have a source in there. So the flow is coming along here like this. And then we have a source at, let's say, point alpha, and that's pushing fluid out. So this way and this way. Now, because and this way, in all directions really. And because we have flow coming in and we have flow going out, at some point here, these two flows are going to meet each other and they are going to result in a stagnation point. So this stagnation point we're going to label B, and this is important as we'll see later on. So as the flow comes along here, it hits this point, the flow comes along here, hits this point, the flow stagnates. Now, the flow in the free stream, the uniform flow, is going to come around and is going to be pushed out because we have the source flow pushing this flow coming out here, and it'll bend around as well. So as a result, we actually have a streamline going through this stagnation point that segregates the outside flow, this uniform flow, bending around the inside flow, this from the source flow. And these two regions, the inside part, which is really all coming from the source, and the outside part, which is really coming from the uniform flow, cannot mix because this streamline here is segregating the two. And we know that anything that goes through this stagnation point has to equal 0 in terms of the velocities, and then hence the stream function will equal a certain amount, and this streamline will equal that all the way along here. So this segregates these two parts, the inside to the outside. Knowing that, what difference does it really make then what happens inside compared to outside? Because the inside now is not affecting the outside other than making this dividing streamline. As such, we can actually say that this streamline here, this dividing streamline, can be treated as a surface. So it's actually a solid because no flow from the outside can get in, so it doesn't really matter what happens in here, and the flow is going to be bending around as if it were an object as well. So we can actually call this the surface now. As a result, we actually have now this semi-infinite body because these streamlines go off to infinity. So we have some kind of object happening here. And let's go through this a bit more and tease out what's happening and how to actually make proper objects. So first of all, the stream function is really easy to do. You can literally just superimpose these two features together. And if you had, let's say, 1,000 sources or 20 sinks or whatever, you can superimpose all of them together, just add them together, these stream functions, and it's completely fine. So the stream function is v infinity r sine theta plus lambda, the strength, divided by 2 pi theta. That is the stream function for this entire flow. Now, we can actually derive what Vr and v theta are because Vr equals 1 on r. We've covered that in this video for the stream function. 1 on r d psi on d theta, and v theta equals minus d psi on dr. And this comes out to be v infinity cos theta plus lambda on 2 pi r. And this comes out to be v minus v infinity, sine theta equals something, constant, or whatever we're looking at. Now, for this point here, B, we can actually calculate what the r and theta coordinates are for this exact stagnation point by setting both Vr and v theta to 0, because we know at this point there's no velocity. The fluid is coming in, stagnating, and actually this is, as a side note, in terms of topology, when you have a flow coming in this way, a flow coming in this way, and then flow coming out these two ways, that is actually called a bifurcation line. So it's segregating the flow. But coming back to this point, we know that Vr here is 0 and v theta here is 0 because the fluid is not moving anywhere. That's this bifurcation line is really like an idealized situation. So we have two unknowns, theta and r, which are the coordinates of this point, and we have two equations. So we can actually find out what the coordinates of b r theta is, and it actually equals lambda on 2 pi v infinity and pi. So r, this coordinate is lambda on 2 pi infinity, v infinity, and theta is pi. So what this tells us is if the velocity is stronger, this point, the distance between b and alpha, the source origin, will become smaller because the fluid is pushing this point towards this point more. Makes sense. If the source is stronger, it's pushing the fluid back more, and the distance between b and alpha becomes greater, so it moves out more. That makes sense. So we can actually calculate what this point is. Now, what about this streamline? Can we calculate what this streamline is? Well, yes, we can calculate that too. So in terms of psi, let's sub in when v r and v theta equals 0 into these 2 points, and we know these coordinates. So sub for r, this into here, and for theta, pi and pi here. So we get psi equals v theta lambda on 2 pi v infinity sine pi plus lambda on 2 pi pi, and this equals a constant, because psi, whenever psi equals a constant, that is just for one streamline, as we covered in the stream function video. And this equals lambda on 2, and that means that this line here, whenever psi equals lambda on 2, that corresponds to this dividing line that is effectively the object's surface. If you wanted to find any other streamline in this flow, you just can set the constant to anything else. You can put it to 5 or 20 or whatever. It doesn't really matter. That will just give you different streamlines around this object. So right now, you're probably looking at this and thinking, well, that's great. We do have some kind of object, but again, it extends to infinity, and nothing is really infinite in real life. We have a pen, it's finite. We have my hand, it's finite. The camera that I'm recording this on is finite. Everything is finite. So there's no really infinite object. How do we make a finite object? Well, before we go any further, I want you to pause this video and think about what we've been going through in other videos up to this point, and think about other fundamental flows. I'll give you a hint. It's to do with the source. So I assume you've paused the video now. You probably haven't, because I never do either. But anyway, at least the thought is there. So in terms of closing this object, we have the front of it. Let's get the back now. We want to suck these streamlines in. So what can we do here? Well, what if we put a sink back here? Let me draw it again so we have a bit more room. So we have the source here again, which is alpha, and we have the stagnation point, which is b. That creates a dividing streamline along as we have the flow coming in. And let's say we put a sink here now, and we're going to call this beta. Well, as the flow comes along here, this streamline is going to get sucked in somehow. And let's say that the streamline, the source is strong enough, the sink here is strong enough that it brings the streamlines in, but not so strong that it actually pulls it straight into the sink, just for aesthetics. But you can do whatever you like. You can put it as strong or as weak as you like. Let's just say it will make the streamlines look like this as the streamlines come around, because it's pulling the streamlines in. And we have another point back here where they converge, and then let's call that D. This one can be C, and this one can be A here. So we have this closed loop based on a source pushing the flow out and a sink pulling the flow in. And if we were to look at the internal flow, which is really non-existent for an actual object, you'd see that there's flow going straight from alpha to beta. But let's not consider that. Let's just look at the outside flow. So from our other videos, we also know that if we have a point, let's say P here, we can find out the angles between the horizontal, which is θ1, and horizontal here, θ2. So let's get the stream function for this entire setup. We have a uniform flow, so we know that we have to add that to the stream function, r sine theta. We have the the source, so let's add that as well, lambda on 2 pi θ1, and we have the sink. Now let's say that the sources and the sink's strength lambda is equal and opposite. It doesn't have to be, but just for simplicity's sake for this demonstration, let's just put that. But again, you can put it as lambda 1 if you like, and lambda 2. Let's just call it the same thing for now. So the sink's contribution to the stream function is lambda on 2 pi θ2. Now if we were to process this a bit more, you'll see that it will start to look quite similar to what we had in the doublet video from last week. So we have theta 1 minus theta 2. And to get a doublet, it's just when theta 1 and theta 2 tend towards 0. So these 2 points get very close together. And this is the stream function for this entire object. And if you wanted to find any other streamline in this point, it has to equal a constant. And again, if you wanted to find out what b is, you would then just differentiate this psi function for v r and v theta, set it to 0, find out what r and theta are, and go from there. Or you can, again, do different streamlines, whatever you like. Now, we've got a completely closed object here, and this actually represents something in real life. It's an oval. We do get ovals in real life. That's great. But as you've probably recognized from even in kindergarten, we do have other objects, not just ovals. We have different shapes. So how do we do other shapes? What about if we want to do a car? If we wanted to do this pen? What if we wanted to do a star? Whatever. How do we approximate different shapes with this idea? Well, there's really nothing stopping us from putting other sources and sinks around this object. So if I were to put a sink here, a source here, it would blow out this point here, and it would actually change where the stagnation point is. Alternatively, if this was a sink, it would pull this section in a bit more. If I were to put a sink here, it would pull this left bottom bit here, put a sink here, this bit again comes in a bit as well. If I were to put a source right next to the other source, it would bulge this bit out again. So now we have a different shape object, and by putting a certain number of sources or sinks around this object, this fundamental object, we can get any shape we want. And we just add the additional components to the stream function, and then we can get a stream function that will describe what the flow is doing around any shape of our object that we want. Now, one thing I need to point out, just if you kind of skipped it in other videos, this is for a 2D irrotational flow, inviscid flow. So it works very well for airfoils and any other streamline object. Not so well for bluff bodies for certain Reynolds numbers. For other Reynolds numbers, it does work very well, and that's certain limitations to keep in mind. But that is how to, in a nutshell, how to combine these different fundamental flows that we've gone through so far to make any object you want and describe the flow around it. So that's in this video. If you liked it, which I really did, this was probably the best video we've done in this series so far because it ties everything together and puts it into a practical point of view. So if you like this, make sure to like the subscribe button, and I'll see you on. Peace, amigos.